Hello, everyone. Thank you for the opportunity that I have to present at the Imprint Conference. My name is Dr. Colin Rogerson. I'm a pediatric intensive care physician at Indiana University. I'm going to be presenting an update on behalf of the Real World Evidence Core for the Imprint network. So the Real World Evidence Core is, again, one of the central cores of Imprint, and our mission is to leverage data from electronic healthcare records to enhance the study of maternal and pediatric health, pharmacotherapy, and precision medicine. Here is pictures of each of the primary members of the Real World Evidence Core team. Starting from the left, we have Dr. Sean Granis and myself, who are from Indiana University and the Regenstrief Institute. Next, we have Dr. Chris Bartlett from Nationwide Children's and Ohio State University. And then we have Dr. Aneda Mendonça from Cincinnati Children's. And then on the right side, we have Medina Sidikanova, who is our project manager. Again, there are more people involved in the real world evidence core, but that is the core group. So what is our vision? Our vision as part of Imprint and how we want to help and support the network is we want to create a large, robust, secure, and accessible data set to fuel maternal child research. So the focus of our research is to help everyone else's research have better resources for real world evidence observational studies. So currently, as part of the real world evidence core, we have 3 large data sources that are all contributing to fuel the Imprint Data Hub. So we have Indiana University and the Regenstrief Institute, Nationwide Children's Hospital, and Cincinnati Children's Hospital and Medical Center. So currently, we have access to all the standard electronic health record elements that are in structured format. So we are able to obtain demographic information, diagnostic codes, laboratory values, medications, vital signs, procedures, kind of everything that's routinely and standardly captured in structured fields in the electronic health record. So these are fairly straightforward to get, and we have access to all these from, again, the 3 institutions that I mentioned. What we've been doing over the last several years as part of Imprint is working on enhancing these data with that are specific to maternal child health observational studies to try and help the Imprint Hub have better data to do better research using real world evidence. So the main 3 enhancements that we've been working on is maternal child linkage, a pregnancy phenotype, and social determinants of health. And I'll go over each of these in more detail. So the first that I'll talk about is maternal child matching. And so the goal of this effort is that we'd like to be able to use structured EHR data to match maternal records to child records. So right now, again, electronic health record data has access to all the structured elements that I mentioned before. But between different medical record systems, it's not a standard that they all have a maternal child indicator, meaning that it's easy to know which childs are maternal records and which are child records and how they are matched together. And so our goal is to develop this indicator to be able to do that. Here's a flow sheet kind of showing what our process has been to do this work. So the data for this came from Indiana University and the Regenstrief Institute. We used what's called the Indiana Network for Patient Care, which is a statewide health information exchange which collects electronic health record data from the majority of the state of Indiana. So starting on the very left, we obtained 82 million records from this database, IMPC. Then we wanted to compare every possible pair of records and see if they are a maternal child pair. So if you do the math behind this, 82 million records ends up being in the trillions as far as possible matches. So what we did is we implemented some blocking schemes and business rules using things like the maternal age, maternal sex, and then blocking schemes such as address, last name, first name, phone number, those types of things. And for a pair to be considered a potential maternal-child pair, they had to meet a certain number of those blocking schemes and all the business rules to be considered by our model. And so what this ended up is we narrowed from the trillions of possible pairs to 6.2 billion possible pairs. Then, moving into the next step, we looked at which of these possible pairs did have a deterministic label embedded in the EHR system. So, for example, some records had put in there that a record was a maternal record and it was paired to a child record, and that was an indicator in the EHR. And so if every record had that indicator, we wouldn't even need to do this work, but the majority of our records don't have those. And so what we did is we took 33 million record pairs that did have that deterministic pair, and then we randomly sampled another 33 million that didn't have that indicator to be negative controls. And this is how we set up our model derivation. So once we had that, then we took all those demographic indicators that were used in the blocking schema. So first name, last name, street address, phone number, and we put those into a probabilistic model to try and teach a machine learning model how to tell if a pair was a maternal-child pair or not. And so we used what's called an XG boosted decision tree model. We did a lot of fine tuning and testing and validation, and we now have what we're considering the final results of that. So essentially, how this worked is we split the test or the data set into 70% training and 30% test data set, and these were the final results. Overall, out of the 30% test data ended up being about 20 million potential maternal-child pairs. There was about 8.7 million that the model correctly predicted were maternal-child links, and there was about 9.8 million that it correctly predicted were not maternal-child links. And then you can see the model got about 1.4 million in possible pairs incorrect. And overall, this leads to final metrics of an accuracy of 92%, a precision or positive predictive value of 98%, a recall or sensitivity of 87%, and an F1 score of 92%. So again, in this work, there's no hard guidelines that say what makes a good or bad model, but in general, these results are very, very positive. We really emphasize the positive predictive value or precision because we wanted to make sure that if the model did determine that two records were a maternal-child pair, that is, we wanted to emphasize that that was the most important thing to be accurate. So you can see that we did sacrifice a little bit of sensitivity or recall in doing this, meaning that there are maternal-child links that the model is missing, but we had to do that at the expense of having a high positive predictive value so that the ones that we said were maternal-child pairs we felt more confident were actual pairs. So what are the next steps in this endeavor? So we have written up our manuscript, and we just, at the week that I'm recording this, we submitted this to JAMIA, the Journal for the American Medical Informatics Association. Well, hopefully they like it and that gets published. As far as imprint goes, we want to test this in an external data set, which will probably be either Ohio State University's data or a combination of Ohio State and Cincinnati Children's, and make sure that it works in other systems as well. And then with the ultimate goal that we take our model and apply it to the entire imprint database so that the whole imprint network has access to a large number of observational records that have a maternal-child indicator that we can be reasonably confident is accurate. Next, I'll move on to the pregnancy phenotype. The goal of this was to use structured EHR data to determine which records had a pregnancy episode at some point in their history. This seems like it shouldn't be that difficult, that there should be a lot of indicators that a woman was pregnant in the EHR system, but as many of you know, it's not actually captured as reliably as we would like. And so that's the goal of this phenotype. So this was not a probabilistic phenotype where we built a model to give a probability that a record contained information regarding a pregnancy. This was a deterministic phenotype, meaning that we built a comprehensive list of features that that our computer scanned for. We looked at diagnostic and procedure codes and laboratory tests, and if any evidence of these were found in any of the charts, then they were determined to have a pregnancy episode. So we took this comprehensive list, we applied it to all the records in the Indiana Network for Patient Care, and created an indicator of pregnancy or not. We then performed manual chart reviews where we extracted several hundred of these records and then looked to see on manual review if they actually had a pregnancy episode or not. And this matrix gives the results. I won't go grid by grid and report the results, but overall, we ended up with an accuracy of 87%, a positive predictive value of 92%, negative predictive value of 85%, sensitivity of 66.7%, and specificity of 97.3%. Overall, it's pretty good. It's not quite as good as the maternal-child matching probabilistic model was, but it does have a fairly high positive predictive value and very good specificity. So if there was no evidence found of someone being pregnant, we don't miss a lot of those. They're pretty accurate. Sensitivity is a little bit poor, meaning that there are likely records that do have had a pregnancy that we don't find with this algorithm. So next steps, we are in the process of getting a little bit more data to finalize the manuscript, and then planning to submit this also to JAMIA. We'll need to validate this in external data, again, likely from Cincinnati or Ohio State, or a combination of the two, and then the goal being that we can apply this to the imprint database. And every record can have an indicator of if they had a pregnancy episode ever or not. The last one, which I'll talk about briefly, is we looked at social drivers of health. We at Regenstrief developed a algorithm called the FORCE algorithm, which uses natural language processing to scan clinical notes and pull out specific social drivers of health elements such as housing, financial, and unemployment data. Our goal was hopefully to apply this to the imprint data set and be able to get these elements. However, we've hit a lot of administrative red tape because the FORCE algorithm is copywritten. It's only available in JavaScript, and most universities don't want to run JavaScript due to security issues. So we're still working through this at this point. So all that said, we have not had any data requests yet come through to us. Again, we're still kind of working on doing these enhancements and building the data set. We've talked about how we can do a front door process request once the data is ready for extraction and queries. We're working on this right now. We kind of anticipate that we'll have an online form. We'll have a review committee that reviews the proposals. The committee will vote, and then we'll give approval or feedback, and then grant access to the data for approved requests. So thank you for the opportunity to give our updates from the Real World Evidence Core as part of imprint. Thank you very much.